Yeah. Ours is super small.
We only fill up 4 desks or 4 tables.
Yeah. My fourth block is all 28 desks are filled when everyone's here. Originally there were 30 in that class.
I can never distribute, right? Like, are you
Well-
supposed to distribute 1, 2, and then also 1, 2, like the other side?
So if I have x plus 2 times x minus 3, this x has to get distributed, and this 2 has to get distributed.
And then you don't have to go back and do the other side because it's already multiplied once.
Well, I've already multiplied the x times both of these and the 2 times both of these.
Okay.
Remember, this is also why if you're not comfortable with that, you can use the area rule and work that way.
Do you find this area in work area?
Or no.
No.
Are you not gonna be here tomorrow?
Oh, I am gonna be there tomorrow, but I wanted to
You
do
just don't wanna risk not turning it in tomorrow?
Yeah. I wanna get out my bag papers. Basically.
Okay.
What page was that? 176.
Well, I'm glad I picked this one to be a bell right here. Apparently we do not remember how to multiply our binomials.
I ain't did binomials in 10th grade.
Huh?
I ain't did binomials since 10th grade.
Algebra 1?
Yeah.
There's one freshman here, I think, for you for Algebra 1. No.
Who beat?
Oh, Algebra 1B, that's right. Yeah,
If you do x times x, would it be 2x or x to the
make
second?
sure you show your work for those kinds of things. Say again?
If I do x to the second, it's simply an x times x.
Correct. Because remember the whole point of an exponent, right? Like when I say x cubed, what I'm really saying is x times x times x. Okay? And so when we have x times x, it's x squared. I'll write that down.
What do I do? Plus, or no, it's like, for the x plus.
So one more time.
What I do, but I write x minus 1
Well, what's being multiplied twice?
x plus.
That's x plus 1 twice. Well, the root might be x equals negative 1, but what I'm multiplying is that times that. One thing to make your life easier in the future, I always simplify that so you don't have to distribute both those x's.
I'll put a 2 right here.
There is still a 2 in front, yeah. Negative 2, isn't it?
Right here, no.
Well, what negative 2x plus 2x, like, go back out into just x?
Are you trying to do, oh, here, I'm trying to
Negative 2 and positive
yes, but I'm not sure how you got that.
2. Because the negative, I had to distribute in the first bubble. And then when I distributed in this bubble, that's something else.
Okay, let,
Oh, those 2 x's, I those together.
gotcha, let's go over this. I'm just gonna go ahead and collect it. Make sure you have the second part filled out. You should be able to identify the degree quickly. So I'm gonna go ahead and collect it and we'll talk about it. Before I officially collect, I do want to point out, so there's a couple of things I went ahead and wrote these notes up on the board. I would write these down if I were you about the even versus odd end behavior. Notice I've only given an example for a quadratic and for a cubic, but every odd function will follow this end behavior. Every even function will follow this end behavior. Every odd function will follow this end behavior. And notice I'm talking about when the a is positive versus when the a is negative. That's a huge thing that we should be able to pull from each of these is I always know what the end behavior is, just based on whether it's odd or even, okay? And so I would probably write that down somewhere as a note that you can study. I'll give you a second to take that down. in a minute, but let's go over this one because we are struggling a little bit with doing the product here. Is that a fair statement? Yep. Okay. So first things first, if you have done the products correctly, if you were to graph the product, what would it look like in respect to the other function? This should be what? The same? So, actually it helps when I open it. First off, degree 3 is what most of us said. Nope, y'all can't see that. So degree 3 is what, oh my gosh, why did it do that? There we go. Change projection mode, duplicate. Can you see my computer now? So degree 3 is correct. Remember it was y equals -2 times x plus 1 squared times x minus 1. So if I were to multiply all this all the way out, what's the highest power going to be? Notice there's 2 here, right? And there's 1 here. So it'd be a total of 3.
Oh, yeah, I got 3.
Does that make sense? Remember, if we write it all the way out, those factors also tell us.
There's 2 x's, squared,
So there's 3 linear factors, so the degree is going to be 3, right? X times x times x. We good on that? Okay. Don't forget when it, now, KJ, you go with that? You look like you're like, going caught off guard. Were you thinking of, did you put 2?
Yeah.
Did you think it was because of this 2? But don't forget it's being multiplied here, so that would give you a third. Okay? So the next thing I do want to point out is, I saw a lot of us trying to do this -2 first. Don't do that. I'm making your life easier by telling you not to do that. Because what's harder is to do this distribution here. I would focus on this distribution. A lot of students try to take this -2 and distribute it to multiple things. Remember, if I had -2 times 3 times 5, would I rewrite that as -6 times -10? No. I'm not going to multiply by both of these in that sense. I'm not distributing. So you don't want to multiply that -2 times both of these as well.
Oh,
You
I'll
want-
leave- I'll leave it to the first one.
Okay.
Well,
Make-
wait, the first
You
one
wanna do it
goes
in the
off.
parentheses first, don't you?
Say that one more time.
You wanna do it in the parentheses or in the.
But can I do x plus 1 first? Like, can I add those together?
No, but you can add both of the parentheses together.
But we're not adding, we are.
Yeah, multiplying them together.
Right. Yeah. So it's just careful with that. So x times x is x squared. X times 1 is plus x. Then I distribute my 1. And personally, right, and so Nathan, I think from here you went ahead and distributed right away, which is totally valid. You can do that. I personally am always going to simplify those like terms first, just to make my life a little bit easier when it comes to the distribution. And then x squared times x and minus 1, so x cubed minus x squared plus 2x squared minus 2x plus x minus 1. So remember, you got to take every single term and distribute it. If you're struggling to identify what is being multiplied by what, what's another thing you could use to help you organize all of these ideas? The box, right? And then you would distribute your -2 from there. But yeah, especially once you get to that the quadratic times the linear. If you want to jump to this and switch midway through, that's perfectly fine. That's going to help you make sure that you don't miss anything. X squared times x is x cubed minus x squared, right? That's exactly what I got here. Plus 2x squared minus 2x, again, exactly what I got here. Plus x minus 1. And then there's my like terms. You just have to then remember that that negative 2 is being multiplied. Any questions about that? Did we just have a brain fart or needed more practice with it?
Yeah, I've never really been good at like distributing, so I don't know. It's just I like I did the -2 first to the first one, so I guess like I just didn't like.
And it can still work out, it just,
Yeah,
it will make it
confusing.
harder, yeah. Okay? I would always leave that distribution until the very end. But again, notice what I said earlier, what I was trying to point out is, if we were to graph that function, it should be exactly the same. So negative 2x cubed minus, was it 2x squared, is that right? Plus 2x plus 2. If I had typed anything else in, would it have perfectly gone on top? No. They're equivalent, right? So we just need a little bit more practice with distributing, so I might build that in with some of the lessons that we have coming up. Let's keep moving though, because we are behind, although we are missing a lot of people today. We'll figure it out. This is the agenda that I have for today. With as many people as we have missing, probably won't do the understanding check today. We'll see. We'll figure it out. I don't know. Yeah. I don't know. We'll do our best to learn. So we already started this lesson 3. This is where we ended yesterday? No, we just finished this number 13, didn't we? This is, what is it?
37,
Okay, so 236, 237? Okay, so a couple of quick things I do want us to notice is, again, and this is why I put this over here, the end behavior alone tells me exactly what kind of, whether it's an even or odd function. How so?
Because if it's even, the arrows are going to be going in the same direction.
If it's even, the arrow's going to go in the same direction. That's a huge thing to notice. And so the fact that both arrows are going down tells me it has to be even. Is the A positive or negative? It's negative. Notice it's going down just like if it was a concave down parabola. So A is negative, right? The slightly trickier ones, because we haven't done as much with it, is the odd end behavior. I do want to point something out really quickly. Has anybody picked up on what the domain of every polynomial has been? Hasn't the domain always happened?
Yeah. The negative infinity positive.
Every single time. Because notice, is it ever going to quit going to the left? Is it ever going to quit going to the right? That's true for evens. Is that true for odds? 100%.
So if on the test or something, you just took the arrows off with that.
Well, even if you look at the graph, like if you look on the calculator, they don't have the arrows, right? It doesn't have the arrows, but what is understood, that it's going to keep going. So even if I don't put the arrows, it's important to recognize like the arrows are there. It's going to keep going forever and ever and ever.
Wouldn't that be negative?
Say again.
Wouldn't that be a negative?
Negative domain.
Yeah, like for number D, for D, wouldn't it be negative infinity and negative infinity?
Remember, what does domain refer to? It's all the what?
Left and right. Yeah.
Left and right. And so you're looking at the arrows, the fact that they're going down, aren't you? And so that's what we want to be careful about is, we're talking about domain, so we're talking about left versus right. So negative infinity, it keeps going to the right as it's going down to positive infinity. So what you're referring to when you think about those arrows going down is, you're thinking about the end behavior. as x goes to negative infinity, what's y going towards? As going to the,
Negative.
right? But then also, as x goes towards positive infinity, as x goes to the right, the y also is going towards negative infinity. So you're thinking about that in behavior when you think about that. Does that make sense for everybody? Any questions? Okay. So that's where we ended. We're going to do a little bit with activity 3.4. We're going to skip 3.3. Actually, I think we already did activity 3.3 in this class. We finished that up. I'm skipping it to my other class. We're not doing the quintic either because that gets wild. So, activity 3.4, what we're going to do, and notice I'm even jumping straight to part C. Use the coordinate plane to sketch each polynomial function. If the graph is not possible to sketch, explain why. So I'm going to do C with y'all and then release y'all to do D and E. So,
I can help with that on that. Is this all on Good Friday?
mhm.
Yeah, I didn't know what was going
Yeah.
on. 'Cause
But I mean, it is taking everything you've learned and putting it into practice. So what do we know if it's an odd degree?
they go the opposite ways.
They go opposite ways, right? So when you're talking about they, what do you mean they?
The arrows.
The arrows, so the in behavior, right? So it increases to x equals -3. So like somewhere in here it's increasing to. And so let's just say it increases to there. Then it decreases to x equals 3. I don't know exactly where, but notice that means I'm just drop it down into here. And then it increases after that. Is that an odd degree? Yep. Does it increase to x equals -3? Yeah. Does it decrease? Yes. Does it increase? Yes. Oh, absolute maximum at y equals 4. Okay, so maybe I could change this to increase up to here. Would that give me that idea of an absolute maximum?
Well, yeah, because
It'd be a relative.
It's a relative maximum.
Definitely relative, right? It's the highest point in its area. So a relative max of 4.
Well, you can't have an absolute maximum.
Why not?
Because it's retaining the arrows.
Oh yeah. Remember, if it's an odd, so remember how we talked about an even degree, the domain is always negative infinity to positive infinity? What's the range always going to be for an odd degree?
The infinities, the negative infinity.
Negative infinity to positive infinity. So can we ever have an absolute maximum and an odd degree? No. And so notice we can sketch it out and try it, but then realize, oh wait, that's not possible. And it's okay to try playing around with it a little bit and realize, oh wait, I can't do that. Right? Impossible to have. Because range is negative infinity to infinity. Right? So I would just probably mark that out instead of redrawing it. So those are the things we want to consider. And so you're doing your best to just fit those features. And that's it. Does that now make sense, Gracie?
Yeah, it's just the way that they do it makes it to where like I don't even know where to start. Like it says the degree. It
Right.
doesn't say like odd or even, it just says like degree 4.
So if it has a degree 4, how many roots are we thinking? 4. Does anyone know how many extrema we should be thinking?
Oh, yeah,
3. Not always, but remember, this is an odd degree. How many degrees would we say this has?
2.
Degrees?
3.
Remember, how many x-intercepts are there?
3.
Right, so there's 3 roots.
So there's like,
So then, how many extrema are there? 2. And so this is something I think I mentioned yesterday, but the maximum number of extrema, not a maximum, but the maximum number of extrema is 1 less than the degree. It's not always going to have that many extrema, but that is the most extrema that are possible. Because y equals x cubed could look like this. Are there any extrema, relative extrema in that case? No. So the maximum number of extrema is 1 less than the degree.
My problem is if it tells me I have like 2 real roots and 2 imaginary ones, I don't know when to put them like question. If I'm supposed to do like real, imaginary, or like real, imaginary, real, you know, like I don't,
It doesn't matter.
it doesn't.
That, so,
But then it gives me the like x is equal to, you know, like positive infinity and this is, and I think I'm gonna get it wrong if I like.
okay, so, does everybody have this for one? Actually, let's do this. I'm gonna look at this one after we do these practice problems, okay? And then I'll go over this one with Gracie, or with the class, so that you can automatically get this homework problem right. But notice, it's just impossible to do this part. So let's work within our small groups on parts D and E. Do your best to figure out a way to make this happen. If it's impossible, explain why it's impossible. Ready to work? Cool. Let's knock it out.
It's 4 examples.
Yeah.
So I think we should do it based off of the behavior right here. 'Cause then we'll know.